Okay, hello everybody. It's an asynchronous assignment for January 12th, and we're going to be talking about linear prediction models. So it's like a line of best fit, and we're going to talk about interpreting the slope and y-intercept in that line, and then making predictions using a least squares regression line, which is the line of best fit. So for linear regression, we're going to take a look at a random sample of students who took a Texas STAR test, Algebra 1 assessment. So this is like a standardized test, and then their attendance rate during that school year. The theory is that the attendance will explain, and then this test score is going to respond. So my explanatory X is the attendance, and the test scores are Y. Let's plot this data and take a look, see what it looks like. So here I can see on the x-axis, I've got percent of schools, school days attended, and then their Algebra 1 test scores. And if I was going to describe this, what I would say is that there is a strong positive linear association between attendance and test scores. The dots are pretty much in a line, they're kind of all together, clearly positive. As attendance percent goes up, the test scores go up. Every mathematician's favorite one-liner is y equals mx plus b. Should be pretty familiar from last semester. So if I look at the equation, y equals 2x plus 1, where's the slope? What does it mean? Where do I see it in the graph, and where do I see it in the equation? So here, this line, it's going up 2 and over 1. Slope is really the change in y over change in x. And in the equation, it's the number in front of the x, the coefficient. And what I would say is that y increases by 2 units for every increase in x by 1 unit. What's the y-intercept? Well, there it is right there, that big red dot. And in the equation, it's this number, 1. So really, it is when x is 0, the y value is 1. So really, the y-intercept is the y value when x is 0. When we look in Algebra 1, we have y equals mx plus b. When we move to statistics or stats, and we have to do a linear regression, the y starts wearing a hat. This because it's a predicted value. It's not an actual value. I have these dots, and really the y represents my predictions. And I usually put the y-intercept first, and then I add the slope for every x, because this is kind of my start, and this is my change, how it's changing each time. Statistics sometimes uses A and B, but we're going to keep the same letters we've been using this year. So here is, here is the line of best fit, and I can see that this one is drawn in here. We're going to talk a little bit more about how this is found mathematically. We're going to rely on a computer program to help us find that usually, but this is right here, line of best fit, and it's going to be my prediction model. When the computer ran this program, they got y hat equals negative 7.69 plus 0.57x. And this y hat, I just say that y is wearing a hat, and this is a predicted value. So in my linear regression equation, this y hat is the predicted y value. There's my y-intercept, and there's my slope. And here in this case, y hat is my predicted test scores, and the x is that percent attendance. Let's interpret the slope. So where is the slope? Well, it's the number in front of the x. In this case, it's the 0.57. And so the slope is, remember, for every 1 unit increase in our x, our models can predict an increase or decrease of whatever the slope is in y. So let's plug in our values. Our y hat is the predicted test score, and the x is the attendance. So basically, for every 1 percentage point increase in attendance, our model predicts an average increase of 0.669 points in the student's test score. So that's the unrounded version. And now let's take a look at the y-intercept. Here it is, negative 7.69. And what is this? This is when x is 0, our predicted y is going to be whatever the y-intercept is. So in this example, if attendance was 0%, our model predicted test scores would be negative 7.689. Now, this y-intercept, this negative value, it's not really meaningful in context. It doesn't really mean anything, because there's anyone with 0 attendance doesn't really go to school and isn't really taking an exam. And this points to something called extrapolations. So when we look outside of our data range, we can get predictions that are not really meaningful. Let's go ahead and take a look at making a prediction. So the superintendent, they want to know if a student meets our minimum attendance goal of 87%, what would their predicted test score be? Well, let's take a look first, go back to that other line, that real simple one, and let's see how we would find a value there. So here, this problem says, find the y value when x equals 2. So what would I do here? Well, I have my equation. There's y, that's what I want to know, equals 2x plus 1. There's x equals 2 on the graph. There's the value I'm looking for up there. So I really substitute 2 in for x. So y equals 2 times 2 plus 1. I multiply 2 times 2, I add 1 is 5. And there I can see where it is on the graph, right? When x equals 2, y equals 5. All right, so let's go back to that superintendent's question. We're looking for 87% attendance. Here's my graph with the regression line on it. That's the line of best fit. Let's go ahead and look and see what happens. Here's my equation. I just rewrote it. Y hat equals negative 7.69 plus 0.57x. There's 87 right there on the graph, right, just after 85. I'm going to substitute in 87 for x. Now I'm going to multiply and add. So if I do negative 0.69 plus 0.57 times 87, I would get 41.9. And I can see that on the graph. That's right where those two, that's right where it is on the graph for 87. So in our next class, we're going to be talking about some of the dangers of making predictions, and we will discuss it using this example. All right, everybody, have a great day.